try to develop a few concentration inequalities together. And these are concentration inequalities that you might have seen in a different class. They have well-known names, as you'll see very quickly. They have to do with Markov's inequality, Chebyshev's inequality, and what we'll build up to is something called Hovding's inequality that we will not prove during the lecture, but that we will develop in the lecture notes. So the basis of most, if not all, concentration inequalities is a result called Markov's inequality. And Markov inequality states the following. It says that if you're given a random variable x, which is non-negative, which means it never takes negative values, it can be 0, but it cannot be negative, and its real value, then for all real valued numbers t, strictly greater than 0, the probability that x is greater than t is less than or equal to the expected value of x divided by t. So before I prove that, it's good to understand what that means. And it's good to understand what probability means when you do a little doodling. I'm going to doodle on the side. I'm going to assume here, just for the sake of illustration, that I have a Gaussian-shaped PDF. Okay, so I have a bell curve here like this. And you can imagine that as a PMF. So I'm plotting x here, and here I'm plotting px of x. Now, once you choose a t, what you are doing is you're choosing an integer, sorry, not an integer, a real number on that line. That's your cutoff. And the probability of x greater than or equal to t is the integral of the density above t, so that's the area in red here. So that area in red here, that is exactly the probability that x greater than or equal to t. Okay, so in contrast, the expected value of x is right here. So Markov's inequality is simply telling you that the probability of having x greater than t has to go to 0 as t goes to infinity, and somehow it's related to the mean. In a way, the smaller the mean, the further t is going to be away from the mean, and therefore that bound gets smaller, and the decay is 1 over t. So again, Markov's inequality is simply a statement about the tail cannot be too big, because at the end of the day, probabilities have to integrate to 1. So if you have a mean, usually a lot of the probability mass has to be concentrated around the mean. It's not always true, but it's a bit of a simplification. But you can understand it as such. The probability mass has to be somewhere around the mean. And if you're too far away from the mean, the probability of being far from the mean has to go to 0. It takes far to go to infinity. That's really the meaning of Markov's inequality. So let's try to prove it together. We're going to develop it carefully. And the reason I'm going through that is because it's not too hard to prove, and at the same time, it's a very good way to get warmed up to using probability in that course. So I'm going to do two proofs. I'm going to first do a proof which is a bit more calculus-based, and one proof that is a bit more abstract-based, manipulating indicator function. They're totally equivalent, but I want you to get familiar with it. The first proof I'm going to do is going to be to bound the expected value of x. Okay, so the first thing I'm going to do is I'm going to use a definition of the expectation. So if I'm assuming that I have a continuous random variable, and I'll leave it up to you to check that everything works fine if you have a discrete one, I can write it as the integral of x, px of x dx. Okay, so here px is my probability density function. Now, what is the range of my integral? A key assumption in Markov's inequality is that that random variable is non-negative, so I integrate from 0 to infinity, not from minus infinity to infinity, 0 to infinity. And what I'm going to do next, I'm going to split that integral into two parts. I'm going to integrate first from 0 to t of x, ex of x dx, plus the second part of the integral from t to infinity of x p of x dx. And now I'm going to try to find lower bounds on these quantities. So the first term, which is here, this integral from 0 to t, I don't know what that is. But I know that x is positive, px is a density, it has to be positive too. And so as a result, I can always lower bound that by 0. Now for that second term here, again, I don't exactly know what it is. I don't know what px is, it's quite general. But I know that in that integral, x is greater than t, because my range of integration is from t to infinity. And so without loss of generality, I can always lower bound x by t and take it out of the integral to get t times the integral from t to plus infinity, dx of x dx. But by definition, this is just t times the probability that x is greater than t. And so if you put all these pieces together, you get a lower bound on the expectation, which takes the following form. It's going to be t times the probability that x is greater than or equal to t. And if you just manipulate that expression, that's exactly Markov's inequality. Px greater than or equal to t has to be less than or equal to e of x divided by t, assuming that t is positive. Now, this is as simple as that. Markov's inequality is super fundamental, but the proof is really just one line. The second thing I want to show you is that there's a faster way of going about that proof, but that requires you to be slightly more comfortable with the manipulation of expectation. Okay? So, if you remember, if you look at the indicator function of x greater than or equal to t, this is the indicator function of a random variable. It's therefore a random variable, but it has to be a binary one, right? Because by definition, the indicator function takes values in 0, 1. And as a result, I can always do the following trick. When I look at the expected value of x, I can always lower bound it by the expected value of x times the indicator function of x greater than or equal to t. And the reason I can do that is because, as I mentioned, this quantity here is between 0 and 1. It belongs to 0, 1. So if you're lucky, you multiply by 1, you don't change the value. If you're not lucky, you multiply by 0, and you reduce the value. Now, when you look at that expectation, you always multiply by the indicator function of x greater than or equal to t. And so as a result, this x is always greater than t. So you can lower bound it by t, which is a constant random variable. And so you can lower bound it by t times the expected value of the indicator function. That tells us that x is greater than or equal to t. And as we argued before, this is just t times the probability that x greater than or equal to t. And that's again Markov's inequality. So the two proofs are completely equivalent. I leave it to you to decide which one you like better. No one is really better than the other. I like the second one because it looks faster. I don't have to write integrals. But it requires you to be comfortable manipulating random variables and indicator functions. And that's Markov's inequality, proved twice in 3 minutes. So Markov's inequality is good in the sense that it tells us something rather fundamental, but it's not super useful as such. In a way, it's too simple. And so people have come up with ways of improving Markov's inequality.